Welcome to Thermodynamics lecture series. In the present lecture, we will discuss the temperature scale and the different types of thermometers. First, we will discuss the temperature scale. A temperature scale is a system of measuring temperature based on a fixed reference and the unit. In general, we are using the different types of temperature scales based on the fixed reference points and the units. First, we will discuss the Celsius scale. Celsius scale is widely used in most countries and in scientific work. In Celsius scale, freezing point of water is marked at 0 degree Celsius and boiling point of the water is marked at the 100 degree Celsius. So in schematically we are representing the melting point of ice at the 0 degree Celsius and boiling point of water is marked at the 100 degree centigrade. So melting point of ice to boiling point of water, that is 0 degree Celsius to 100 degree Celsius, is divided into 100 equal parts and each part is 1 degree Celsius. Next we will discuss the Fahrenheit scale. Fahrenheit scale is widely used in the United States. In the Fahrenheit scale, freezing point of water is marked at 32 degree Fahrenheit and boiling point of water is marked at 212 degree Fahrenheit. So this is the schematic representation of the Fahrenheit scale. So here observe the melting point of ice or freezing point of water is marked at 32 degree Fahrenheit and boiling point of water is marked at the 212 degree Fahrenheit. So difference between the melting point of ice to boiling point of water is 180 degree Fahrenheit. So scale is from the melting point of ice to boiling point of water is divided into 180 equal parts and each part is 1 degree Fahrenheit. Next we will look for the Kelvin scale. Kelvin scale is in general used in science and engineering. In Kelvin scale, freezing point of water is marked at 273 Kelvin and boiling point of water is marked at 373 Kelvin. So this is the schematic representation of the Kelvin scale. Here observe the melting point of ice is marked at the 273 Kelvin and boiling point of water is marked at the 373 Kelvin. So difference between the melting point of ice to boiling point of water is 100 kelvins. So this 100 kelvins is divided into the 100 equal parts and each part is 1 Kelvin. Next we will discuss the relation between the Celsius scale and Fahrenheit scale. So in Celsius scale, melting point of ice equal to the 0 degree Celsius and in Fahrenheit scale, melting point of ice equal to the 32 degree Fahrenheit. So we can be written as melting point of ice equal to the 0 degree Celsius equal to the 32 degree Fahrenheit. Similarly, boiling point of water equal to 100 degree Celsius equal to the 212 degree Fahrenheit. Next we will look for the relation between the Celsius scale and Fahrenheit. For this we will discuss the ratio equation. Ratio equation is the which relates the position of a temperature between freezing and boiling in both of the scale. So here capital C is the Celsius scale and capital F is the Fahrenheit scale. Tc represents the temperature in Celsius scale. Tf represents the temperature in Fahrenheit scale. So next we relate the Celsius scale and Fahrenheit scale by subtracting the 32 from the Fahrenheit, which aligns its 0 point with the Celsius scale. So Tc equal to the Tf minus 32. Next we are dividing by 100 to Celsius scale and similarly dividing by 180 to the Fahrenheit scale, which gives the Celsius scale per degree and Fahrenheit scale per degree. So this equation we can be written as Tc by 100 equal to the Tf minus 32 divided by 180. This can be written as Tc by 5 equal to Tf minus 32 divided by 9. So finally we can be written as Tc temperature in Celsius scale equal to 5 by 9 Tf temperature in Fahrenheit minus 32. So this is the very important equation. Please remember this one. Next we will see the example problem on the relationship between the Celsius scale and the Fahrenheit scale. At what temperature Celsius and Fahrenheit are equal? Option A minus 25 degrees Celsius. Option B minus 30 degrees Celsius. Option C minus 40 degrees Celsius. Option D minus 35 degrees Celsius. So here option C is the correct. So we will see the explanation. We know the relation Tc equal to 5 by 9 Tf minus 32. Let's consider, so temperature on a Fahrenheit is minus 40, then Tf is the minus 40. Then Tc equal to 5 by 9 into the minus 40 minus 32. So it is equal to the Tc equal to 5 by 9 into minus 72, which is equal to 5 into minus 8, which is equal to the minus 40. So here we are considering the Fahrenheit temperature is the minus 40. Then temperature on Celsius also we got the same temperature of minus 40. So option C is the correct. Next we will discuss the gas thermometer. Before that one we will discuss some basic introduction regarding the ideal gas. The name only indicating ideal gas. An ideal gas is a theoretical gas which is composed of many randomly moving point particles that do not interact with each other except when they collide elastically. It is a simplified model used in thermodynamics to understand. So ideal gas is the composed of many randomly moving point particles, and here assumption is these moving point particles do not interact with each other. So this is the assumption in the ideal gas. From the experimental observation, it has been established that an ideal gas behaves according to the simple equation, that is the PV equal to mRT. Here P is the pressure, V is the volume, T is temperature, and small m is the mass, and capital R is the gas constant, and units of the gas constants are the joule per kg Kelvin. And this PV equal to mRT can be written as P nu equal to RT. Here nu equal to V by small m, which is the specific volume. Its units are meter cubed per kg. And PV equal to mRT can be written as P equal to rho RT, rho equal to small m divided by volume, capital V. It is the mass density. Its units are kg per meter cubed. And here capital R is the gas constant. Its units are joule per kg Kelvin. So this gas constant capital R can be written as R bar divided by capital M, and R bar equal to the universal gas constant. Its units are 8.314 joule per mole Kelvin. And capital M is the molecular weight of the gas. Its units are the gram per mole. So PV equal to mRT can be written as PV equal to small m into R bar divided by capital M into capital T. And this can be written as PV equal to R bar small m divided by capital M into capital T, temperature. And we know that one, small m divided by capital M, which is represents the number of moles. So that is representing in the small m. So small n equal to small m divided by capital M, and which is also we can be written as small n equal to number of molecules divided by Avogadro number, that is capital N by capital A. So this equation we can be written as PV equal to N R bar T, and N also we can be written as capital N divided by capital A. So PV equal to capital N into R bar divided by capital A into the T. So which is equal to the PV equal to NKT. Here K is the Boltzmann function constant, which is equal to R bar divided by capital A. In reality, there is no gas which can be qualified as an ideal gas or perfect gas. However, all gases tend to ideal or perfect gas behavior at all temperatures as their pressure approaches zero pressure. So we know ideal gas equation is the PV equal to mRT. For the two states of the gas, this PV equal to mRT equation can be written as, for the two states, P1 V1 by T1 equal to P2 V2 divided by T2. So from this equation, T2 divided by T1 equal to P2 by P1 into V2 by V1. Now we will discuss the gas thermometers. Among the gas thermometers, we will discuss the constant volume gas thermometer. The basic principle of the constant volume gas thermometer is, at constant volume, the pressure of a fixed amount of gas is directly proportional to its absolute temperature, which means capital P is directly proportional to the capital T at a constant volume. So temperature is measured by observing the pressure of the gas at a constant volume. So now we have to see the brief details of the constant volume gas thermometer. Here figure shows a schematic diagram of a constant volume gas thermometer, and a small amount of gas is sealed inside a bulb which is labeled as capital B, which is connected to one side of a mercury manometer capital M through a narrow capillary tube capital C. So here observe the diagram. Here gas is sealed inside the bulb and bulb is labeled as the capital B, and this bulb is connected to the manometer capital M through the capillary tube which is represented as the capital C. And one more thing you have to observe from the diagram. Other side of the manometer is open to the atmosphere and it can be raised or lowered to adjust to the mercury level, so that it just touches the tip capital L of the capillary. So here observe by the diagram, other side of the manometer is open to the atmosphere and mercury level is raised or lowered by adjusting the pressure of the gas. And pressure of the gas in the bulb, which is depend on temperature, and this pressure is used as the thermometric property, and pressure value is given by the P gas, pressure of the gas inside the bulb, equal to the atmospheric pressure P atmospheric plus rho m G jet. Here rho m is the density of the mercury, capital Z is the difference in mercury level. So this is the capital Z. When the bulb is brought in contact with the system whose temperature is to be measured, the bulb in course of time comes in thermal equilibrium with the system. Then gas in the bulb expands or being heated, pushing the mercury downward. The flexible limb of the manometer is then adjusted so that the mercury again touches the lip capital L. So let's consider we want to measure the temperature of the hot water. Now this hot water is the system whose temperature is to be measured. Then contact this hot water with the bulb. Due to the higher temperature of this hot water, gas inside the bulb also heated and it will be expands. During expansion of the gas, this gas is exerted the pressure on mercury. This lead to pushing the mercury downward at the one side of the mercury. Then due to this flexible tubing, other side of the mercury it will be rises. Then the difference between the mercury level, that is capital Z, is recorded and the pressure P of the gas in the bulb is estimated. Since the volume of the trapped gas is constant, then from ideal gas equation we can be state that PV is directly proportional to the capital T. So here V is the constant, then change in pressure, that is the delta P into V equal to the capital R into the delta T, that is the temperature differences. Then this temperature difference, that is the delta T, equal to V by R into delta P. So here stated that when the temperature increases is proportional to the pressure increases. By using this equation we will be calculate the change in temperatures by recording of the change in pressure with the constant volume gas thermometer. Now we have to see the constant pressure gas thermometer. In a constant pressure gas thermometer, mercury levels are adjusted to maintain constant pressure and the changing gas volume with the temperature. is served as the thermometric property. So in a constant pressure gas thermometer, thermometric property is the change in gas volume with respect to the change in temperature. Then change in temperature delta T equal to P by R into delta V. So here the temperature increases is proportional to the observed volume increase. But in general, the constant volume gas thermometer is mostly in use because of it's simpler in construction and easier to operate when compared with the constant pressure gas thermometer. Next we will discuss the electrical resistance thermometer. Electrical resistance of most of the metals increases with the temperature. So this property is utilized to measure the temperature. The relationship between the resistance and temperature is usually linear over a small range, which means resistivity of the metals increases with increases in temperature and resistivity of the metals decreases with the decrease in temperature. So in a resistance thermometer, the thermometric property is the change in resistance of a metal wire with temperature. So the figure is shown the resistance thermometer. So here observe a thin wire, generally we are using as the platinum wires, is wounded in a coil and placed inside a protective sheet. The leads are connected to the Wheatstone bridge circuit to detect the small changes in resistance. In general, Wheatstone bridge is an electrical circuit used to measure the unknown resistance very accurately by balancing the two legs of a bridge circuit. And this Wheatstone bridge is measuring the small changes in resistance due to temperature changes. Now we place this platinum wire at different temperature conditions such as the standard temperature environment and the temperature which is to be measured environment. Then we have to use the following equation to measure the change in resistance, that is capital R equal to R naught into 1 plus AT plus BT square. So here R naught is the resistance of the platinum wire when it is surrounded by a melting ice and A and B are the constants. Next we will discuss the thermocouple. A thermocouple measures temperature using the thermoelectric effect, in which a voltage is produced at the junction of two dissimilar metals when exposed to a temperature difference. Here refer the diagram which represents the thermocouple principle. Here see thermocouple circuit made up of joining of the two metal wires. One is the wire A, another one is the wire B. These are made of the two dissimilar metals. So here two dissimilar metals are exposed to a temperature difference by maintaining the at the one end is test junction temperature, another one is the reference junction temperature. So now two dissimilar metals are exposed to different temperatures, then voltage has to be produced, and this voltage is varies with the temperature and can be measured to determine the temperature accurately. And thermocouples are commonly used due to their simplicity, durability and wide operating temperature ranges. Due to the Seebeck effect, a net electromagnetic force EMF is generated in the circuit, which depends on the difference in temperature between the hot and cold junctions and is therefore a thermometric property of the circuit. This EMF can be measured by using a microvoltmeter to a high degree of accuracy. The choice of the metals depends largely on the temperature range to be investigated. In general, copper constant and chromium aluminum and platinum rhodium are typical combinations are using. A thermocouple is calibrated by measuring the thermal EMF at various known temperatures and the reference junction should be kept at 0 degrees centigrade. The results of such measurements on most thermocouples can usually be represented by a cubic equation in the following form, that is epsilon equal to A plus Bt plus Ct square plus dt cube. Here epsilon is the thermal EMF and the constants A, B, C and D are the different for the each of the thermocouple. And most advantage of this thermocouple is it comes to thermal equilibrium with the system whose temperature is to be measured quite rapidly because its mass is very small. And these are the details of the different types of the thermometers, and thank you.